And here we are. Ladies and gentlemen, the final section that we're doing on statistics and data analysis is about sample sets of data. All right? Sample sets of data. All right? In this section, we are going to be analyzing populations. All right? So, and population doesn't necessarily mean group of people, but it could be a population of, right, whatever data we might be analyzing. Okay, so population of deer, all right, it could be a population of bank accounts, it could be population of planets in our solar system, whatever it is, okay? So a population is not necessarily a group of people, but an entire set of items being considered. So let's consider that. Population, here we come. So population is an entire set of items or people, etc., right? In a group being considered. And I don't know if you guys are aware of this, but any sort of surveying or gathering of data or trying to calculate how many deer are in the Green Mountain that are over the age of 2, they don't actually track down every single individual and get their information. Right? I don't know if you were aware of that. We don't
track down the deer and ask them how old they are.
Right, exactly. They'll take a portion of the population and then infer things about the entire population.
So it's like a lot.
No, well, we can actually get more and more confident assumptions about an entire population the larger the sample that I take. All right, so for instance, actually just the other day at my house, around dinner time, I had a representative from the United States Census Department come to my house, knocked on my door, and he's like, I have a list of randomly selected addresses. We don't even know who lives there, and I just have to come in, ask some questions, and gather data, right? So he wasn't stopping by and visiting every house in Windham County. He would select random ones, right? And then ask those people questions. And once he hit a certain number of them, he then could assume that, okay, I could say that, the mean salary per year in Windham County is whatever amount. And it's based off of, that original sample, but we'll extrapolate that information to the whole population. Okay? So, in order to do this, what you need to have is a random sample. Okay? So, a random sample is a subset of the population. Okay? And it's really important that it's random. Okay? Let me think. For instance, what if I was surveying students at the school, and I wanted to figure out how many of them exercise in any capacity, for at least 1 hour a week. And I'm, trying to find, I don't want to ask every student in the school this because it'd be a pain. So I'm just going to find a portion of the population. But what if I chose to ask, hey, the baseball team's out there today. I'm just going to go ask the baseball team. Do they exercise an hour a week at least, right?
No.
But that wouldn't be a good sample of the population. They're not representative of the whole population, right? It would really skew my data, right? It would really throw off my numbers. I'd end up coming up with assumptions that would not be true, all right? The key is that it has to be random.
Chess club as well.
But even that could skew my data, right? I'd have to find some way, I'd be okay, maybe what I'll do is just stand by one of the entrances of the school and ask the first 50 people that come through the door, right? And assume that that would be random enough that I would get, both athletes and non-athletes and kind of get a good...
Athletes,
What?
If you're doing it random. What happens if you do it we get all athletes even though you're doing it random?
Right, then that's something that I'd have to be aware of before I crunch my numbers. However, the larger the sample that I pick, right, if I just pick Actually, let's look in this room. All right. Let's say I've got how many people? 1, 2, 3, 4, 5, 6, 7, 8, 9, including me. And I said, okay, I'm going to sample this population. And let's say I pick 2 people out of the 9. And I want to figure out what percent of this population is currently wearing just a t-shirt, right? And I sample these 2 guys, and they're both wearing t-shirts. And now I'm saying 100% of everyone in this room is wearing a t-shirt. All right? That's not true. But as I increase my sample size, right, now if I get 3 guys here, right, 2 of them are wearing t-shirts, 1 isn't, I could say, aha, 2/3 of the population is wearing a t-shirt. And the larger I increase my sample size, the more accurate my assumptions will become. I will become more confident in the data that I'm presenting. So if I sample 100 people or 1,000 people or 1,000,000 people, I can get more and more certain regarding the accuracy of my results. Because it's unlikely, I mean, we just covered a chapter in probability, it's unlikely that the first 4 or 5 or 6 people I pick all happen to be the only people wearing t-shirts, right? There's a chance that could happen, but with probability, I kind of can come to some degree of certainty that I'm at some point going to get a sample that represents everybody pretty well, okay? So like that's the idea. The larger the number of people I interview or use as my sample, the better the accuracy becomes. And that's one of the things we're going to be talking about today. And so this activity of using a subset of the population to make statistical conclusions about the entire population is called inferential statistics. Like I'm inferring things. Inferential statistics. Right? So it's where I use information from a sample, use info from a random sample, hopefully random, to make predictions about the population. Right? Right, so like another example of not a good sample would be, what if I wanted to figure out what is the average GPA in the school, and what if I only showed up to like the AP, calculus class, or the AP, right? What is there? Is there an AP US history class or something like that? Like if I only sample a particular portion, it's going to really skew my data, right? It's going to throw things off. And actually, that's one of the things I had told the U.S. Census guy, because one of the things he calculates is, what is the average distance people travel to work? And so I told him, I was like, man, I'm really going to skew your numbers, because I walk like 100 yards to work, And he's like, well, actually, I also interview people that work from home, So he's like, so they don't even have a commute. So their distance is 0, theoretically, right?
Bed to desk.
Yeah, bed to desk, right? So yeah, so like that's the sort of thing, right, to be aware of. So that's inferential statistics. Now, a couple of things we're going to consider here is there is the true mean of the population, okay? So the true mean, all right, which we're not going to have, all right, is the mean of the actual population. Because the best I'm going to be able to do is to find the mean of my sample. I'll know that for certain, right? But if I found like the average height of the people in this room and I surveyed only 4 people, I could only give you for certain what the average height is of those 4 people. And then I could kind of expand it with some assumption to the population. But there is an actual average height of the people in this room. There is a true mean of that number. I just won't know it. Right, so the mean of the actual population, and it's abbreviated by this Greek letter mu. All right, so it's kind of like this weird, like little curvy M thing.
Ocean.
Yeah, sure, little ocean waves there. So it's the Greek letter mu, and it represents the true mean of the population. And so I'm going to have my, so x bar is the mean of the sample. And I'm going to try to figure out how likely is it that mu is within a certain range of my x bar. Okay? That's one of the things that we're going to try to figure out. And the way we do that is with this. It's called the standard error of the mean. All right? And I guess I can write down this actual. It is the standard deviation of the distribution of the sample means. All right, and this is abbreviated by the symbol. It's sigma sub x bar. Right, so this is read as, actually I usually do verbal things in white here. So this is sigma sub x bar. Right? Or the standard error of the mean. So it's going to represent how likely is it, or what is the distribution of the true mean about my sample mean. So kind of a little weird. And this behaves exactly like a standard deviation because it is a standard deviation. It's just measuring not the distribution of my data values in my sample, but it's measuring the distribution of possible true means is essentially what it's calculating. So there's a formula for sigma sub x bar. And sigma sub x bar is calculated by this. You take sigma and you divide by the square root of n. So sigma is the standard deviation of our sample. And n is the size of our sample population. N is the right. So if I interview 100 people, then n is 100, right? And the greater n is, actually, let's just analyze that for a moment. So if n is 100, I'd take the square root of 100, which is 10, and divide sigma by it, right? And that would give me a number regarding the distribution of the true mean about my sample mean. But the greater that n is, all right, what happens when I divide? Well, actually, let's think about this. If I have a pizza and I've got 8 friends, divide that pizza into 8 slices. Those slices are okay in size, right? Right, decent sized slices. What if I have like 20 friends? Now those slices are getting even smaller. Or what if I've got like 30 friends, even smaller? Or 100 friends?
That's a lot of friends.
It's a lot of friends, and not a lot of pizza per person that they're getting, right? Or let's say, I don't know, let's say I've got 1,000 friends in one pizza, and I'm like, you guys are gonna love me. I'm sharing my pizza with everybody, right? But they're like, oh, thanks. Like, it'd be like, a little sliver of a slice, like, right? So the idea is the larger the number I divide by, the smaller the answer becomes. So the more people I interview in my sample, the smaller that distribution becomes, and my true mean is got to be getting like even closer to my sample mean, right? And with that, I'll be able to figure out, well, what's the likelihood that I'm 99% sure that the true mean is within this range. And I'll be able to say that. All right? So, like, I'll be able to have a level of confidence is what we'll talk about later. So, let's do some actual math. I've only been talking about terms and such. So let's do this. So let's find the standard error for x bar equaling, well, actually, no, never mind. Not x bar. Well, we'll get there, but let's start with if sigma is, let's say the standard deviation is 2, like a problem we had earlier, and let's say n, the population that I'm interviewing, let's say it was 100. And I guess I'll throw x bar at us, why not? Let's say x bar was 24, kind of like the problem we had earlier. Kind of exactly like the problem I had earlier. Actually, I like that line, like when musicians are going up to like play at an open mic and they're like, my next song goes a little something like this. I like it when they say, my next song goes exactly like this. Because technically it does. Exactly.
Not a lot of songs.
Yep. Right, so this is exactly like the problem we just had earlier. So let's see. So let's calculate some stuff. So sigma sub x bar is going to equal what?
2 divided by 10.
2 divided by the square root of a hundo.
Which is 10.
2 divided by 10, thank you, sir.
Plus 5.
Which is 1/5
Oh, right.
or 0.2. So what that means is, means. Actually, my best friend used to call his cat Mewy, and he would write her name with the Mew symbol. It's pretty great. Pretty great. Mewy. So let me just draw 2 graphs here. So here's 24, 26, 28, 22, and 20, right? And then this one's also going to be at 24, but it's a little bit different. So this is the distribution. Wrong color. Blah. This would be the distribution of my values. Okay? So this is the distribution of the actual data. Let's see. That F showed up funny. Right? So you could answer me like, oh, 68.3% of your data is between 22 and 26. Right? You'd be able to answer all sorts of things like that. Whereas this distribution, because this 0.2 actually behaves like a standard deviation, that means that 1 sigma sub x bar away, I'm going to have 24.2. 2 sigma sub x bars away, I'm going to have 24.4, right? 1 sigma sub x bar prior to the mean will be 23.8, and then 22.6. Nope. Oh, it's switched colors even. 23.6, right? Sace. And so, look at what this ends up looking like. Now, these are exactly the same curve. Well, I tried. But notice the scales are entirely different. In fact, actually, let me redraw this curve in green or something like that. So this is a distribution not of my data. Man, why did I lose my data there? DATA, there we go. This is a distribution of possible locations of the true mean. And as a result, I'm able to now say something like, I am 68.3% sure that the actual average of the population is between 23.8 and 24.2. All right? Yeah. So I'm talking now about where is the true mean, and I don't know what the mean of the population is, but look at, like, that's kind of a close range, right? Like, that's kind of a close range. And if I was to try to, I can actually, if I wanted to, graph these both on the same plane. So let's see, 23.8 and 23.6 would be like there and there. So that means this graph on this would look like this. I messed up right at the end there.
Oops.
Noob. So basically, I end up getting a really narrow standard deviation, but the sigma sub x bar is able to let me say things, like, I'm 96% shorts between these two values, or different things like that. And that's where, like, voting polls and stuff like that, I don't know if, like, you've seen that as, like, elections are live. Before they've actually counted everyone's vote, they'll say, like, Barack Obama has, like 47% of the votes, and Mitt Romney has whatever percent, and they'll be like, there's like a, within a margin of like error of like 1% or 2%. So like they've got a sample of the population of like the current votes that have come in, and they can say, we're pretty sure that these are the actual percentages of the nation represented here with like a 1% margin of error. Right? So they're able to kind of express that confidence. And I want to point out, what happens if I divide it by 1,000 here? Yeah, then the square root of 1,000 would be even larger than 10, right? Well, actually, if I make it 10,000, then it'd be 100. Actually, let's do that. Sigma sub x bar, my equal sign didn't show up. 2 over the square root of 10,000. Right? So that's 2 over 100, or 1 over 50, or that's 0.02. So that would mean these values would be like 0.02, 0.04, and I'd be even more certain of the range, right, of which my true mean lies. Okay? So the larger the sample I get, the more accurate and confident I become. All right. So let's assuming the values for the first one. What if I end up asking the question? So what range? I guess let's see, how would I phrase this? Within what range would you be 95% sure certain that the true mean lies there?
That'd be two standard deviations away, right?
Well, I think 2 standard deviations is technically 95.5% or something like that.
5.44.
Yeah, something like that. So let's actually figure this out. So what do I know? I know my p-value is 95%. So what I'm going to do, I'm going to look up my p-value, and now these typically I'm dealing with t-values here. All right, where I want a range, so like an above and below sort of thing. So t, looking it up, here we go. Looking up t-values when it's the p that you know. Man, that was the best intro song ever. So here's my p-value, t-value. So I scroll down to 0.95, and I get 1.9599. I think we did call it 1.96 earlier is what we called it. So t-value 1.96. So that means 1.96 sigma sub x bars. All right? Above and below the mean, I will be 95% certain that the true mean lies in that range. Okay? So let's actually figure out what that range is. So I'll do x bar. Actually, I'll put this in green. X bar plus or minus t times sigma sub x bar. That's weird that there's like 2 x bars showing up there. Right? Where sigma sub x bar is the standard error of the mean. Blah. So let's plug this in. So what do I have? I've got 24 plus or minus 1.96 times, what is sigma sub x bar? for my original? 0.2. 0.2. So 24 plus or minus, let's see, is my calculator still up and running? It is! 1.96 times 0.2. 2. Do. So that's 0.392. So that means 0.392 units above and below my mean. I'm going to be quite certain here. Quite certain. So I'll do 24 minus 0.392. And I get 23.608. 2 and 24. I'll do second entry. Why not? Do the old switcheroo on that minus sign. Know what I'm saying? Yeah, I guess yeah. That's what you get. So what does this mean? That means I'm 95% sure that the true mean of the population is between those two values. Right? And those are pretty close together. And if I wasn't comfortable with that, I'd have to get a larger sample. Right? But that's the idea. It's not that bad. It's no es más mal.
No, está mal.
Oh, okay. Sorry.
No está mal.
No está mal?
No es tan mal.
Están mal?
No es tan mal.
This is our
I'm not doing very well here.
It's easy. It's
Yo.
no. You know how to say no?
Yo hablo español el más mal del mundo.
Kind of.
No hablo.
No, you do pretty good.
So let's see. Here we go. So now a couple other things I got to teach you is level of confidence. And we've actually already done this, which is nice. I just did it, and I didn't tell you what we was doing. Level of confidence, abbreviated LOC. All right, works like this. So if I have a level of confidence of 1%, 1% LOC. Now that's what's weird about this is this sounds opposite of what you think. It means I am 99% certain. Okay? So that means P would equal 99%. All right? Whereas if I have a 5% level of confidence, which is what we had just done a moment ago, that means I am 95% certain that the true mean lies within that range, right? So P is 99%.
So it's just 100 minus the...
Yeah, so it's kind of the opposite of what you think. Thank you.
You're welcome.
Blah, blah. All right. So let's do one more example, I guess. So let's say I don't know. Let's say our average height is let's say 60 inches. I don't know. Is our average height?
5 feet.
Nope. All right. We'll do 68 inches. I don't know. Yep, you're all set.
Okay. We'll see the big package.
And let's say sigma that we calculated was, I don't know, 2. Right? So some of us are shorter, some are taller. Right? Something like that. I don't know. And let's say I sampled, all right? Let's say I sampled all of us in here. Well, there's actually one less person. They just walked out.
You just
Leave in class.
walk out on you.
Yep. So what I want us to do is find the range with a 1% level of confidence. Okay? So let's say I sampled all of us in here, but I wanted to figure out what is the average height of people in the whole school, or in the whole town of Wilmington, or I don't know, Vermont. Who knows? Holy smokes. So 9 people probably wouldn't be a very good number if I was going to make those sorts of assumptions. But here we go. So let's, what can I do? What should I do first? What should I do, ladies and gentlemen?
Well, P equals 99%.
Yep.
So then you go on your little chart thingy, bobber.
To find my t-value.
On your P value.
And for 0.99, I get a t-value of 2.576. But I think we're a little bit early here. I think we got to find something else first.
Oh boy.
Because if I use this with that sigma, that will give me the range for which 99% of the people are those heights.
Divide the 2 divided by the square root of 9.
This guy's got it, right?
That would be 2 divided by 3.
So 2 divided by the square root of 9. I got to find sigma sub x bar. I'm not interested in the distribution of my data values. I'm interested in the distribution of where the true mean lies. We're looking for Muey. Is Muey hiding under the bed this time?
2
Behind the
divided
couch? In the
3.
cupboards?
Mu's impossible to catch.
Mu 2. So 0.6 repeating roughly is the sigma sub x bar, right? So I'm looking for the range that has a 1% level of confidence. So what am I going to do? I'm going to do x bar plus or minus the t times the sigma sub x bar. And what do we get?
68.
So 68 plus or minus 2.576. And what's cool is this this t-value, the number of standard deviations, applies whether I'm talking sigma sub x bars or whether I'm talking actual standard deviation of my data value.
0.6 repeating. 0.6 repeating, which then equals I have no order.
Right? So let's figure that out a little bit. So that's going to be 68 plus or minus.
Can you roll up a little bit?
In un momento.
Thanks.
1.7173 repeating. I'll just call that 1.7173.
Oh, I see what you did there because you can't do repeating, so you have to put in division instead.
Well, I rounded. Yeah, that's what I did. Yeah, yep, exactly. And then 78. Oh, it's yelling at me. So 68 plus 1.717.
69.7.
Slow down, friend. How are you doing this? Are you like a wizard with math? 69.7173. Uh-oh, where's my cursor? There we go. Uh-oh, where's my color? Oh, yikes. That's class. Well, anyways, your homework's on the board. Take it from there. I don't know why this is not writing.
Oops.
That's really weird.
30.
Well, I'm calling it. You guys are good. Have a good day, ladies and gentlemen.